Here we go. Mark your own. Oh, gotta have my favorite student. A says, find the magnitude of the force. Now, why didn't I say magnitude and direction? I'll explain in a little bit. But first of all, to find the force between two charges, it's K Q1 Q2 over R squared. It's going to be 9 times 10 to the 9th. Negative 5 microcoulombs or positive 5 microcoulombs? Do I put the negative in here? How do I know? Okay, so you need to look at your formula sheet. I used to make kids memorize all this. You're the first year that I've actually put the absolute values on the sheet. I used to just have the kids track it themselves. So it's going to be 5 microcoulombs, 3 microcoulombs. And R is, looks like 2.35 squared. Is that correct? So the force is going to be, this is probably not going to work out evenly, 9 times 10 to the 9th, 5 microcoulombs, 3 microcoulombs divided by 2.35 squared. The magnitude, is it 0.0244, blah, blah, blah? I'm going to write that in scientific notation. I'll go 2.44 times 10 to the negative 2 newtons. Now, before I go to part B, what if I had asked for the direction? I would have to tell you which charge we were talking about. What direction is the force on charge 1, on Q1? Is Q1 feeling a force to the left or to the right? Because like charges repel and unlike charges attract. Both of these charges are feeling a force inwards, so Q1 is getting pulled to the right, Q2 is getting pulled to the left. What if I had a third charge right there, and I called it Q3, and I said find the net force on, I don't know, Q2. I would find the force between Q1 and Q2, like I just did, magnitude and direction on Q2. I would find the force between Q3 and Q2, like I just did, magnitude and direction, and then I would add them vectorially. If the directions were the same, I'd just add them. If the directions were different, I'd go winner minus loser, bigger minus smaller. I like B, I like B, I like B. B says, find the electric field, magnitude and direction at location A. To find the electric field from two charges, we find the electric field from the first one, we find the electric field from the second one, and then we add them vectorially. Electric field is going to be KQ over R squared. So the electric field from charge 1 is going to be that. It's going to be 9 times 10 to the 9th. Also positive. We don't include the negative here. And it's going to be 1.5 squared. This might work out evenly. In fact, I think it will. Is it going to be 30,000? Hang on, let me double check. First of all, let's try this again. 9 times 10 to the 9th, 5 microcoulombs divided by 1.5 squared. The 5 will cancel. One of the 3's will cancel. Isn't it 20,000? Is that right?
Yes. Yeah.
20,000. Yes. Okay. Wow. Brain. Squared. I was doing, yeah. Anyways, units, newtons per coulomb. You could say volts per meter. That was the new units we learned for electric field yesterday, but since we used the force equation, I'd rather do it that way. Here's the key. Direction. How do we figure out the direction for electric field? We imagine a little positive sitting at our location, and we ask, which way would a positive want to move because of this guy? Which way would a positive want to move because of Q1? To the left or to the right? To the left. Or west. I repeat, for charge 2, it's going to be 9 times 10 to the 9th. It's going to be 3 microcoulombs. Yuck, this is not going to work out evenly. Over 0.85 squared. I chose to just backspace and edit because I have a good calculator. 0.85 squared. And I got 37,370 newtons per coulomb. Direction. Which way would a positive sitting right there want to move because of this guy? Also to the left. How do I add left plus left? Just add them up. If they were in opposite directions, Pierce, I'd go winner minus loser. But here, I think I do this in my head. It's going to be 57,370. Yes? 57,000. I'm going to go 57,400 newtons per coulomb left. I'll give you 1 mark for the magnitude, 1 mark for the direction. But if you got it right, 2 out of 2. Devin, what does C want me to find?
Electric potential.
Oh, okay, so I'm going to go like this, right? Or am I? Is that electric potential? What's that? Electric potential energy. You can't get them mixed up. Here's the problem. I can find the electric potential energy from that diagram. In other words, if I get the terms mixed up, there's nothing in the question itself that will give me a roadblock along the way where I can say, oh, I'm finding the wrong thing, but I would have to give you 0. What's another word for potential? Begins with letter V. I'm going to find the voltage from charge 1. I'm going to find the voltage from charge 2, and I'm going to add them up. The voltage from charge 1 is KQ1 over R. In fact, I think, if I'm lucky, I got that and just got to delete the squared. It's going to be 9 times 10 to the 9th. Oh, do I include the negative here? Okay. Negative 5 microcoulombs divided by 1.5. So here, I really should go d, insert the negative. And I get negative 30,000 volts. Direction. Isn't any. It's a scalar. Okay. What does that negative 30,000 tell me, by the way? Again, if that charge wasn't there, it's telling me that if I put a 5 coulomb charge there, that 5 coulomb charge would have negative 150,000 joules of energy, because it has negative 30,000 joules of energy per coulomb. That's what voltage means. If I put a 2 coulomb charge, if I put a positive 2 coulomb charge right there, it would have negative 60,000 joules of energy. I would have to do positive 60,000 joules of work to move it out to 0 because it wants to fall down. I'll repeat this for the second charge. It's going to be 9 times 10 to the 9th, positive 3 times 10 to the negative 6, divided by 0.85. This isn't going to work out evenly. However, I think if I sneak back here, I can just do that. I get positive 31,764.7. How do I add these? Tip to tail? Nope. Just add them. I mean, really, I can do this in my head. Oh, not plus 30,000, Mr. Duick. Minus 30,000. It's going to be 1,764 volts. I'll go 1,760 volts. If you got that, 2 out of 2. Otherwise, I would give you half mark for that, half mark for that, and 1 mark for the answer. If you missed the negative, if you told me the answer was 61,760, I would give you 1 out of 2. Then I would go to the next page. For this question, I said it was worth dulping. So we have a fixed charge right there of negative, wow, negative 8 microcoulombs. And we're starting with an electron very far away. Wow. We're starting the electron really far away, and then we're moving it to a final location 0.15 meters away. This is asking me how much work. Well, work equals the change in potential plus the change in kinetic. I think I can do that. I don't see any indications of speed. So this is going to be PE final minus PE initial. Are any of these 0? Well, a very long distance away is code for infinity. I wouldn't have to start a very long distance away. Devin, if I wanted to just make this question a little bit harder, I would maybe start 3 meters away, and you would have an initial potential energy. But okay. Potential energy is K Q1 Q2 over R, and so this will be R final. Here we go. 9 times 10 to the 9th. Q1, I put the negative in. Q2, it's an electron. Negative 1.6 times 10 to the negative 19. And R final was 0.15. And this is nice because what's a negative, Connor, times a negative? I do get a positive work. I would, by the way, because this is a negative fixed charge. As I'm pushing the electron closer and closer, I'm having to push harder and harder and harder because this is repelling it. So I am having to do work. What do I get? 9 times 10 to the 9th. Did it again, Mr. Duke. Negative 8 microcoulombs. Don't do that. Read your equations carefully because they do all look alike. Negative 1.6 times 10 to negative 19 divided by 0.15, no squared. Do you get 7.68 times 10 to negative 14? Is that right? I would give you 4 out of 4 for that. Otherwise, I'd probably go 1 mark for that, 1 mark for canceling out the potential energy initial, 1 mark for the numbers, and 1 mark for the answer. And then I would turn the page over. This is asking me to find a speed. Henry, here, this is like falling, except we're falling up. But this is a job for conservation of energy, G. I'm going to go kinetic initial, potential initial equals kinetic final plus potential final. Are any of these 0? It does say that we start out at rest. Are we ever out at infinity? If I wanted to make this question easier, I could have asked Emily, how fast will it be going when it reaches infinity? But I didn't. So I'm going to get this. K Q1 Q2 over R initial, not squared, equals a half M V final squared plus K Q1 Q2 over R final, not squared. And Devin, I think what I want to find is that I could get the V by itself. It's overkill. Instead, I'm going to subtract that to that side first. I'm going to get K Q1 Q2 over R initial minus K Q1 Q2 over R final, and that equals a half MV squared. It's V final, but since I only got one V, I dropped the F because it's the only one I'm finding anyways. K, 9 times 10 to the 9th. Q1, positive 5.5, isn't it? Microcoulombs. Q2, it's a proton. Divided by R1, 1, minus ditto mark times ditto mark times ditto mark divided by, what's R final? Careful, it is not 2.5. It's 3.5 because it's the distance from the fixed charge. It's that distance right there. Very common mistake, and I like this question. I like this. There is going to be at least one question on your test where I give you a picture in this format, and in fact, if it's multiple choice, one of the answers will be using an R of 2.5 because kids just read the numbers instead of thinking, oh no, it's how far away it is. So 3.5, that equals a half mv squared. 9 times 10 to the 9th, 5.5 times 10 to the negative 6. It's a proton divided by 1. I know dividing by 1 doesn't make a difference, but I also know I'm going to backspace and edit, so I'll stick it in there anyways. 7.92 times 10 to the negative 15. Minus, this next one I doubt is going to work out evenly. Yeah. 2.263 times 10 to the negative 15. That equals a half mv squared. Is that right or wrong? Good? So it's going to be 7.92 times 10 to the negative 15 minus, answer button. And I get this, 5.6571, blah, blah. I'll write 5.657, but store this on my calculator. Times 10 to the negative 15. 5.6, what did I say it was? 57. That equals, well, instead of writing a half mv squared, I'll write it as mv squared over 2. Final step, Connor B. How do I get the v by itself? There's an m, divide by, times by 2, divide by m. Which m? It's a proton. Okay, so I don't need to tell it to you. So you're telling me it's going to be the square root of 2 times my answer button divided by, I know a proton is 1.67, but I can never remember the 10 to the... Negative what? Sorry?
27.
So it's 6, 7, and 27. That might be a dumb way that I can remember it. I mean, I can always look it up too. 2 times answer button divided by 1.67 times 10 to negative 27. Let's make sure I type that right. What the? Oh, square root. Come on. Square root, answer button. Do you get 2.60 times 10 to the 6th? If you got that, 4 out of 4. Otherwise, I'd probably do something like this. Half mark, half mark. I'd probably give you half mark for that number, half mark for that number. That's 2. I'd give you 1 for that, half for that, and a half for the answer, or something like that. But again, as always, if you got it right, 4 out of 4. Hope that adds to it. 1, 2, 3, 4. Yeah, there we go. And then there was a mistake in this. I can't remember if I pointed it out to you folks or not. I hope I did. But it's negative 5.5. I wrote negative 5.5 in the question, but on the diagram I didn't. If you used the negative 5, I will give you full marks for that one too. And if that explains why 2 of you might have been getting different answers and barking at each other and thinking each one was right, I have to be honest, I find that such a pleasurable thought, I don't regret making the mistake at all.
No, we got the same. We just picked everything else.
Oh, okay. It's a job for conservation of energy. Are any of these 0? Well, it says we're going to come to a stop. Are any potential energies 0? Are we starting at infinity or ending at infinity? No. Would be nice. So I'm going to get this. A half m V initial squared plus K big Q little q over R initial equals K big Q little q, or Q1, Q2, over R final. And I guess what I'm trying to find is R final. You know what? I'll get this whole left side by itself as a number first, then I'll get the R final by itself. So it's going to be a half mass. It's an electron. It is an electron, isn't it? Yes, it is. 9.11 times 10 to the negative 31. Oh, I also made up dumb numbers for this question too, because I think you end up moving barely at all. Like, I think you end up at like 4.93 or 4.94 something. So next year, if you flunk my course, I've made the electron going faster, and this time it travels like 2.6 meters or something. But okay. Anyways, I made the velocity too small. I didn't give it enough kinetic energy. 6.8 times 10 to the 6th. By the way, the gravitational analogy is I didn't throw it very hard, and so it didn't go very high before it came falling back down. Yeah, I needed to give it more kinetic energy. Should have thrown it harder. Don't forget the squared. Plus 9 times 10 to the 9th. Negative 5.5. Negative 1.6 times 10 to the negative 19. All over 5 equals ditto mark. .5 times 9.11 times 6.8 times 10 to the 6th squared. I think you get that for the first term, but actually I decided to be bold and do this all in one line. So I just kept going. I went plus, is that right? Half mv squared. Yeah, that is. I went plus 9 times 10 to the 9th times negative 5.5 times 10 to the negative 6th times negative 1.6 times 10 to the negative 19. I divided that by 5. Can you double check me? Did you all get somewhere along the line of 1.605 times 10 to the negative 15th as your summary step? No? Yes? Yeah? A couple of you nodding? Okay. 1.605. That equals K Q1 Q2 over R final. So I guess that means R final is going to be K Q1 Q2 all over the answer that's stored on my calculator. It's going to be K Q1 Q2 all over my answer button. Any typos? I think I look good. No, I'm wrong.
You used 5, not 5.5.
Arg! Arg! All over 1.6050622 times 10 to the negative 15. I didn't do the correction. Well, that was dumb of me. There's the 4.93 that I knew we were going to get. So it ends up moving about 7 centimeters, which really isn't much at all. What? No?
We did it the other way. With
The other way.
5, and we got the exact answer.
The same answer as us? Here? It could very well be that it's not enough to make a difference. Let me ponder for a second. Because I know, you know what it is? Okay? You're timesing by the 5, not the 5 here, dividing by it here. Those would cancel, and this is so small compared to this that it hardly makes any difference. I didn't give enough kinetic energy, and so because the big Q's, although they technically don't cancel, if this is really small, they'll almost cancel because this is hardly just a bit of a fudge factor. Then yeah. Hey, can you give yourself a score? Oh, sorry, 4 marks for that. Do I need to break down part marks, or are you okay with that one? Okay, part marks. I'd probably go something like this. I'd go 1 if I saw that. Definitely give you 1 mark for that. 1 and 1. I did a wimpy job of part marks. Can you give yourself a lovely score out of 18, please? Lawyers, angels. I got -2 when I did it too. I just wrote that down wrong. I'm sorry. -2 for number 1. I'm sorry. Did I start recording to fix this, Mr. Dewick?
Nope.
I did, yeah. I turned the recorder back on. Sorry, folks. -2. I wrote the wrong answer down because I'm apparently coughing. For Emily, if you go to my website, and if you click on Principles of Math 12, which is what Pre-Calculus 12 used to be called, you click here for screencasts. I did a pretty good job of teaching combinatorics. So here's trig. Oh, by the way, here's all the logarithm stuff that you guys have done. Here's all the transformations, slides, reflections, all that stuff that you guys have done. And combinatorics starts right here, the fundamental counting principle. Permutations with repetitions. Combinations, which is NCR. Permutations is NPR. There you go. The binomial. I don't know if you guys do the binomial expansion theorem anymore, but it's way cool. Pathway problems, because they're way cool. And it looks like I did. I probably have, if you click here. Oh yeah, tutorials. I probably have video tutorials. I got a bunch of log ones. Oh yeah, there's a couple of combinatorics reviews there. My most recent one is probably my best one. I've been talking to you, Mackenzie, about parallel plates, and I've tried to tell you that they are lovely. What? They are lovely because they make the math much easier, and they're also going to allow us to explain lightning. So recall from last lesson, we said that if you take 2 pieces of metal plates, and you put them parallel to each other, and you charge one to be positive and one to be negative, you get an electric field. Which makes sense, because if this is positive and this is negative, a positive would feel a force down, a negative would feel a force up. If it feels a force, there must be an electric field, because I've told you that's what's exerting the force. That's how we get away with that action at a distance nonsense that allows witchcraft and magic. I've said to you, the way that we are exerting forces on objects without touching them is we are touching them. It's just with something that's invisible. It's a field. And we ended up with electric field being that. By the way, there should technically be a vector on that. Who in this class volunteered to get shocked with the Van de Graaff generator? Who were my shock? Okay, so if you can remember roughly how far the spark jumped, if you remember how far it went between your hands, roughly, later on I'll show you how you can figure out how many volts it was approximately. That's one of the things we'll do today. It's fairly easy. Example 1 says this: explain why an atom will be ionized. In other words, the electron will be pulled off of the atom if it's placed in a sufficiently large electric field. First of all, Taylor, what direction is the electric field according to this arrow? Don't overcomplicate it. To the right. Which way would an electron feel a force then? Yes, because electric fields are defined as which way positives would feel a force. We have to define it somehow. So we said, let's talk about it in terms of positives. So an electron would feel a force in that direction. What would that force be? That force would be calculated by going QE, where Q is the electron. But if I make that electric field big enough, now there is a force holding the electron on the atom. What force is that? What's the charge inside a nucleus? Positive. And what's the charge on an electron? Negative. It is attracted to the nucleus. It wants to stay where it is. But I'm telling you, if I put a big enough electric field on there, large E, that means large force, and I can rip an electron off. Very easy to do. We can even do it to air molecules. So if we're talking about air, which is mostly nitrogen and oxygen and other trace gases, but it's mostly nitrogen and oxygen, it turns out the electric field required to rip an electron off of an air molecule is about 3 million volts per meter. Is volts per meter an electric field? Oh yeah, that was the new units that we learned yesterday. It was not only newtons per coulomb, volts per meter also worked. If you put air in an electric field of about 3 million volts per meter, you'll create a spark. One electron will jump from one air molecule to the next, 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 to the next. You'll create an arc, you'll create a small current, you'll create the equivalent of a wire, but out of air. And this happens frequently. This 3 million volts per meter may seem like a lot, but in actual fact, ionization of the air occurs frequently. It's the crackle we hear when we pull apart clothes that come out of the clothes dryer. You may have heard that on a dry day. It's the shock that we get when we walk across a carpet on a cold winter day and then reach for a doorknob. Lightning. Push pencils down, look up. Let me introduce you to John Travoltage. Okay? So John Travoltage, when he walks on a carpet, he can rub electrons off of the carpet and they gather on him. Now, where will they gather? Like charges. So they'll try and gather on a dry day. If you're building up static charge, it'll try and gather on the outside of your skin. That's why you may feel the hairs on your skin standing up. That's why you have that weird, what you think of, Mackenzie, as that weird, dry, staticky feeling. It's probably the hairs on your skin standing up because they're trying to repel each other. Okay? And if he builds up a big enough charge, a big enough electric field, 3 million volts per meter, it can jump. So let's build up more charge. He's built up a lot of charge. As we decrease the distance.
Ouch.
Okay? There was enough electric field to ionize that distance of air. And so that's what happens when you get a shock when you walk across the carpet on a dry day and you reach for a metal doorknob. It's also what happens with lightning. Each of these shocks is accompanied by light. And the reason is when the electron jumps to a neighboring atom, it doesn't just stay free. It wants to settle into an orbit and it has to lose some energy to do so. Energy's got to go somewhere. It goes into light energy. So it's also a little conservation of energy. Put your pencils down, look up. Let's talk about lightning. Although a cloud kind of looks like this, thunderheads typically have a fairly flat bottom, and so you can kind of imagine that it's one side of a parallel plate. And you can treat the Earth, although it's technically curved, you can treat it roughly as a straight line as the other side of a parallel plate. Which means what we've just learned can be applied to lightning. So it says this: suppose the bottom of a cloud is charged to a positive voltage of 2.5 times 10 to the 8th volts. Where does that charge come from? We think it comes from cosmic rays coming through the atmosphere. They pass their energy onto the cloud because the energy's got to come from somewhere, and voltage is energy per coulomb. How close does the cloud need to be to the ground in order for lightning to occur? Keep in mind that air ionizes at around 3 million volts per meter. That's a rough value. Humidity changes that number. Temperature changes that number. But 3 million is a good average. Connor, what does this question want me to find?
How does the cloud need to be?
How close?
Oh.
How close? What's that? What variable would that be? Distance. We learned yesterday between parallel plates that electric field is the voltage divided by the distance for plates. Connor, my friend, could you get the distance by itself, please? Yeah, you.
Times the D over divide the D.
So, over E. So the electric field, it's about 3 times 10 to the 6th. That's the electric field that you need in order to ionize the air, for the spark to start to jump. The voltage, if you have a bigger voltage, by the way, you can have a closer distance, so it all depends on how much voltage you have built up in the cloud. Here it says it's 2.5 times 10 to the 8th. How close does this cloud need to be to the ground for lightning to occur? I'm going from memory. I didn't do this one in my head. I think you get 83.3 repeating. Double. Is it right? Okay. 83.3 meters. What if the cloud was 85 meters above the ground? Could lightning occur? What if you were standing there? Well, then your head will close that distance enough, and rather than hitting the ground, the lightning will hit you. This is how human beings get hit by lightning. They enter a situation where the lightning is almost but not quite, where the voltage built up in the cloud is almost but not quite enough to mesh with the electric field and jump the gap, and you inadvertently, without realizing it, close the distance. By the way, who got shocked with the Van de Graaff generator? Get the V by itself. How would I get the V by itself? Times the D over. So if we go on our calculator, 3 million, because I know that the electric field required to jump is about 3 million volts per meter. If I go 3 times 10 to the 6th, how big a distance were you guys getting your shocks? Was it about 5 centimeters? So let's go times 0.05. You're pulling about 150,000 volts. If you're one, that's how I was able to give you some rough guesses, estimates as to what the voltage was. So when we had the really, really small shock, I said, yeah, it's probably about 20,000, 30,000 volts or something like that. There's a lot of variance. I can't remember, on our day, was it rainy or was it dry when we did it? Do you remember? No one does. Okay. You used to be my favorite class. So based on what I've just told you, where would you not want to be in a lightning storm? Well, first of all here, because if you're standing there, the tree has dramatically reduced the distance required, and then the lightning would travel down the tree and arc through the ground into you. Not a good thing. You also would not want to be hiking in the mountains, and now I got to go serious. For those of you that are outdoorsy people, if you are ever hiking somewhere and you notice that it's thunderstormy conditions and you start to feel that staticky feeling where your hair is starting to stand up, and I'm being dead serious, yell at your friends, get their attention, and you need to run or jog down to a lower altitude. Not walk, run or jog. You are right there at the threshold. You are right close to being able to complete that circuit. Get out of there. Okay? There's my Mr. Duick's public service announcement for science. Every year, people get hit by lightning in the mountains. Why? They've decreased the distance required. Now, a boat is also a bad thing to be in for two reasons. Water is a lousy conductor. Wait a minute, Mr. Duick, I thought water was a good conductor. Pure distilled water is a lousy conductor. But water with impurities in it, i.e. all water in nature, is a really good conductor. So anything with salt or dirt or minerals, which is anything in a lake or a river or the ocean, is a really good conductor. So if lightning hit there, it would travel through the water into the boat. And then some boats have a metal mast, which dramatically decreases the distance. So don't be in a boat either. Put your pencils down, look up. Recall that if we know the field, the electric field, we can find the force by using QE. On your blue sheet, can you find that equation? No. On your blue sheet, can you find where that equation came from? Yeah, it comes from Mackenzie, our definition of electric field, which was that one there, and if I get the F by itself, we're good. So now we have an equation to find the force between parallel plates. Because if I go F equals QE, and if between plates I've said that the electric field is the voltage divided by the distance, so This equation is on your formula sheet. Yes? It seems to me that I can combine these two. I can say the force on a charge between plates is going to be the size of the charge times the voltage between the plates divided by how far apart the plates are. I would put that on your blue sheet. It's not on your yellow sheet. It's a combination of two equations, which I think is reasonable to expect. But if you want to, as a little note, make a note on your blue sheet where it came from, because I absolutely guarantee you might be asked for that on a test, or to use it. And here's the beautiful thing. The charge that we're moving is a constant. It doesn't change during this question. The voltage, well, that's what you've charged the plates up to, which doesn't change during the question. And how far apart the plates are isn't changing during this question. This force here is a constant, not a changing force. And oh my goodness, some math became much nicer then. Turn the page. Pierce, what are they asking you to find in the next question? What did I just finish talking about quite a bit? Force, you say? Is there an equation that has force and acceleration in it? Oh, hey, here we go. So example 4 says, find the acceleration of an electron that's placed in between metal plates that are separated by 2.5 centimeters and charged to 275 volts. Which way will the electron move, by the way? Which way will it accelerate? Kiana? Yeah, towards positive, away from the negative. Which way did a proton accelerate? Down. Okay, so the first thing I'm going to write for this then, Pierce, is F equals QE. That's sort of on your formula sheet, but not quite. Except F equals what? I'm now going to write MA equals Q. And what's the electric field between plates? That's also on your formula sheet. It's the change in voltage divided by how far apart they are. Oh! Pierce, how would I get the A by itself? The physics here is physics 12. I would argue the actual math is physics 11, fairly trivial. We're plugging two different equations into one big one. Meh. But you have to know that they're there, and as Devin has shown us earlier, they also all look alike. It's easy to get them mixed up with squareds and not squareds. So just be careful, be careful, be careful. So you're telling me that the acceleration is going to be QV divided by the mass times d. Q. It's an electron. Now, am I going to put the negative in or not? You know what? Do I want a positive or a negative acceleration? I'm going to ditch the signs. The answer is technically you should put a negative in, but also technically the voltage should be negative because voltage is defined in terms of which way a positive would want to move if it could. And this is a negative electric field because, you know what? I want a positive acceleration. So I'm going to kind of just cheap out here. And I'm going to say 1.6 times 10 to the negative 19. 275 volts according to the picture. Mass. It's an electron. I know an electron is 9.11. I can never remember the 10 to the... And the distance is 0.025. We don't do physics with centimeters. You're going to get a big acceleration. Do you get 1.93 times 10 to the 15? Yeah? Isn't that faster than light? Wait a minute. Is this a speed? Did we find what did we find? Acceleration, okay? If this electron starts from rest, you can actually calculate this and travels 2.5 centimeters with that acceleration. You can find V final. I would use VF squared equals VI squared plus 2AD, and you'll find it's nowhere near the speed of light. That distance, which does appear in the equation, it can't get faster than light. The universe is still taking care of itself. It's got massive acceleration, but relax, Einstein is still right. If I ask you for a direction, which way is it going to accelerate in this question? Up. Because towards the positive, away from the negative. This idea of having a charged object between plates is how we figured out the charge on an electron. This is where that 1.6 times 10 to the negative 19 came from. In a very famous experiment, Millikan used parallel metal plates to hold in place a charged metal drop. It was a droplet where gravity was pulling it down, and he'd let electric force push it up, and he let it hover. So he knew the two forces were equal. And from that, he was able to solve for Q. So as an equation, this is a job for a free body diagram, Mackenzie. What are the forces acting on this drop? Get the obvious one. Mackenzie, what are the forces acting on this drop? Get the obvious one. Yep. And then we have an electric force pushing up. And if we cause it to hover, then Mackenzie, I can say those two forces are the same. In other words, as an equation, I'm going to get this. Fe equals mg. Except, wait. QE equals mg. Right? Yep. Wait. Q change in voltage over distance equals mg. And in his experiment, he knew the mass very accurately. He knew G, 9.8. He knew the voltage because he knew what he was hooking it up to. He measured the distance very accurately. And what was he able to solve for? Then he used Avogadro's number to figure out how many molecules and therefore how many atoms and therefore how many extra electrons there were, and was able to get the charge on one electron. Very clever. I'm assuming most of you have done some chem and remember Avogadro's thingy. Okay. We are kind of, sort of, almost out of time here. Example 6. What are they asking me to find in example 6, Henry? It's exactly the same as example 5, where you'll say the forces are, look up, the forces are the same. QE has to equal mg, and electric field is voltage over distance. What are they asking you to find in example 6? Times by D divided by Q, and Bob's your uncle. And I'm just going to skip that because I've gone almost the whole class. Lightning is cool, and I always get off on tangents and talk about it too much. What's your homework? What are number 5? Number 4 is asking you to find what force. I would start with QE, and then I would say, oh no, it's Q voltage over distance. It's straight plug and chug, but you got to derive the equations. What's number 5, Brisa, asking us to find? I'm telling you, since the force is constant, you can go force times distance. 8. It's asking you to find the electric field, the force, the acceleration. We've done all that. And then it's asking you to find V final. Don't overcomplicate it. You can use VF squared equals VI squared plus 2, physics 11 to find V final. You don't know T, so you can't use VF equals VI plus AT. You can solve for T. 9. Same question as number 8. 10. 11. 13, 14. I know I've thrown a lot at you, but this is crucial stuff. Oh, and then it does say at the end of the lesson, video, car. I showed you the car video already, so